Good afternoon, everybody. My name's Luke Chapman, and I'm doing my presentation on titanium. Intro. I'm doing this presentation on titanium, and I'm going to go into detail about everything that involves this metal. Titanium is a special metal that has a unique characteristics. I'm going to share a bunch of different ways that titanium is used in today's society. And this picture is an example of the titanium rock in its ore form. The physical properties of titanium. Titanium is widely distributed and constitutes of 0.44% of Earth's crust. The metal is found combined in practically all rocks, sand, clay, and other soils. The specific gravity of titanium is 4.5. Hardness of titanium is 70 to 74. Hardness Rockwell B. The tensile strength of titanium is 240 megapascals. Young's modulus of titanium is 120 gigapascals. And titanium is a very lustrous, silvery white metal with a low density. It has high strength and is excellent corrosion resistance. So that means titanium does not rust. Physical properties continued. High strength to weight ratio. Titanium is as strong as steel but significantly lighter, making it very ideal for applications where weight is a crucial factor. It has excellent corrosion resistance due to the protective oxide layer that forms on its surface. Titanium is highly resistant to corrosion from seawater, chlorides, and many other corrosive environments. High melting point. Titanium has a very high melting point around 1660 Celsius, and this allows it to withstand extreme heat. Titanium also has a low density compared to other metals with a similar strength. Titanium has a relatively low density. Non-magnetic. Titanium is not attracted to magnets. The ductility. When pure, titanium can easily be shaped and formed into different shapes due to its ductility. Biocompatibility. Titanium is considered to be biocompatible, meaning it is well tolerated by the human body, and it is often used in medical implants. Titanium does have poor thermal conductivity, though. Compared to other metals such as copper and aluminum, titanium has relatively low thermal conductivity. Chemical properties. High corrosion resistance. Titanium's primary chemical characteristic is its remarkable resistance to corrosion due to a protective oxide layer that forms on its surface. Reactivity at high temperatures. While relatively unreactive at room temperature, titanium readily reacts with oxygen and nitrogen at high temperatures, even burning in pure nitrogen gas. Oxidation state. The most common and stable oxidation state of titanium is 4. Reaction with acids. Titanium is resistant to most dilute acids, including hydrochloric and sulfuric acids, but can be attacked by concentrated hydrofluoric acid. Low thermal expansion coefficient. Titanium exhibits a relatively low thermal expansion coefficient, meaning it is less prone to distortion due to its temperature changes. Formation of compounds. When reacting with oxygen, titanium forms titanium dioxide. And titanium is resistant to most acids and chlorine. This is the chemical properties continued. Titanium has a density of 4.51. Titanium's melting point is, like I said before, 1660 Celsius, and titanium's boiling point is 3287 Celsius. Mechanical properties. Titanium has many mechanical properties, including tensile strength, modulus of elasticity, and fracture toughness. We'll start out with fracture toughness. Many titanium alloys have a high fracture toughness, which means that they resist crack propagation very well. The fracture characteristics of titanium alloys are affected by changes in the microstructure. Hardness. Commercially pure grade 1 titanium has a Rockwell B hardness of 70 to 74. The hardness of industrial pure titanium with the highest purity is usually below 120 Brenwell hardness. Commercially pure titanium has a strength to weight ratio, making it ideal for high temperature applications. With a melting point of around 3034 Fahrenheit and a density of approximately 4.5. It is commonly used in components subjected to extreme conditions. Now, when titanium is exposed to air, it forms a thin layer of titanium dioxide that protects it from the rust. This layer is a self-healing and very tough. Titanium is resistant to corrosion from salt water. Titanium is often used in aerospace and medicine because of its durability. Titanium is the least tarnishable metal, and titanium is biocompatible and has a high strength to weight ratio. Other properties. Strength. Titanium is comparable in strength to steel, but it weighs significantly less. Density. Titanium has a density of about 4.5, which is 60% of that of steel. Corrosion resistance. Titanium is resistant to corrosion in seawater and chlorine and is immune to microbiological influence corrosion. Titanium's low density and high strength to weight ratio make it the material of choice for many corrosive chemical environments, including oxidizing chloride solutions, including seawater, and chlorine-based bleaches. The material processing. The material processes that I'll be discussing is the mining process, refining process, and fabricating process of titanium. Let's get started with mining. Regardless of the final usage, titanium must be removed from its ore and turned into pure titanium. This is done by processing titanium oxide, manufactured from either ilmenite or rutile through the Kroll process. The output is a titanium sponge, which is purified, melted, and alloyed with other metals. The process of mining and processing titanium involves extracting the ore from the earth, purifying it, and then alloying it with other metals. Titanium is primarily found in the minerals ilmenite and rutile. The ore is crushed and washed to separate the titanium-bearing minerals from other materials. Titanium is extracted from titanium ore using the Kroll process, magnesium reduction, and emerges as a sponge titanium. The next process is the refining process. Titanium refining involves extracting titanium ores, purifying it, and shaping it into useful products. The Van Arkel's method is used for preparing ultra-pure metals by removing all the oxygen and nitrogen present in the form of impurity in titanium. In this method, crude titanium is heated in an evacuated vessel, which is iodine at 523 kelvins. The covalent titanium tetraide thus formed is separated. The titanium is purified by high-temperature vacuum distillation. The metal is in the form of a porous granule, which is called a sponge. This may be processed on-site or sold onto other companies for conversion to titanium products. What is the new process of refining titanium? These days, titanium is now made from the Kroll process, in which titanium dioxide is reacted with chlorine to form titanium tetrachloride, which is then reacted with magnesium to strip away the chlorine and leave behind the pure metal. Fabrication. The main production process for titanium metal is known as the Kroll process. In this process, the main ore, known as the rutile, is treated with chlorine gas to produce titanium tetrachloride. This is then purified and reduced to a metallic titanium sponge by a reaction with magnesium or sodium. Quality testing procedure and standards. Titanium quality testing procedures and standards include chemical analysis, non-destructive testing, and mechanical testing. Chemical analysis. This determines the reliability and performance of the metal. It checks for structural flaws, assesses how the metal will withstand harsh environments, determines how manufacturing processes will impact the metal. Like for other metals, the most important standards for titanium are US ASTM and SAE, or more specifically, the aerospace part of AMS, European Euro norm, German DIN, Japanese JIS, International ISO, as well as Chinese GB and Russian GOST. Mechanical testing. Purpose: this evaluates strength, hardness, ductility, and tests toughness. Methods: tensile testing determines yield strength, ultimate tensile strength, and elongation. Hardness testing measures resistance to deformation. ASTM E18 for Rockwell hardness and ASTM E92 for Vickers hardness. Impact testing assesses material toughness under sudden force. ASTM E23 for the Sharpe impact test. Corrosion resistance testing. Purpose: it ensures titanium resists corrosion, especially in marine and medical applications. Methods: salt spray testing, which is ASTM B117. Electrochemical testing. Standards for it is ASTM G28. Pitting and crevice corrosion testing of stainless steels and titanium. ASTM G44 is the exposure of titanium and titanium alloys to high temperature water. Fatigue and fracture toughness testing. Purpose: determines the material's durability under cyclic loads. Methods: rotating, bending, fatigue test. Fracture toughness test is the ASTM E399. Standards is the ASTM E647, which is the measurement of fatigue crack growth rates, and ASTM E1820, which is the fracture toughness of metallic materials. The eddy current testing, which is ASTM E309. Purpose: it confirms tolerances and surface quality. Methods: it coordinates measuring machine, which is CMM, laser scanning, and surface roughness testing, which is ASTM B244. Key industry standards. ASTM standards: ASTM B265, titanium and alloy steels. Sheets: ASTM F136 is medical grade titanium. ISO standards: ISO 5832 is implant grade titanium, and ISO 9100 is aerospace quality. AMS standards: AMS 4911, which is titanium sheet and plate for aerospace. Industrial applications. Titanium is used in many industrial applications, including aerospace, automotive, chemical processing, and medicine. Aerospace. Titanium's strength and light weight make it ideal for aircraft and space vehicles. Titanium's heat tolerance makes it well suited for jet engines. Automotive. Titanium's light weight and resistance to high temperatures make it ideal for high-performance components such as exhaust systems, engine valves, and suspensions. Chemical processing. Titanium's corrosion resistance makes it a good choice for heat transfer applications in chemical plants, refineries, and other power plants. Titanium's corrosion resistance also makes it a good choice for drum washers, bleachers, and various pumps and piping systems in the pulp and paper industry. Medicine. Titanium's biocompatibility and corrosion resistance make it a good choice for medical and dental implants. Additive manufacturing allows for the production of patient-specific implants with intricate designs. Industrial applications continued. Due to their high tensile strength to density ratio, high corrosion resistance, and ability to withstand moderately high temperatures without creeping, titanium alloys are used in aircraft, armor plating, naval ships, spacecraft, and missiles. Today, about 2/3 of all titanium metal produced is used in aircraft engines and frames. As an example, the A380 Airbus uses approximately 70 tons of titanium for the aircraft structure and fittings. Titanium in medical devices. Titanium is one of the most biocompatible metals the human body can handle. The human body can handle it in large doses with no impact. In fact, it is estimated that we ingest around 0.8 milligrams of titanium a day. Most passes through us without being absorbed. Also, its density is very similar to the human bone, which will readily adhere to it. These qualities make titanium alloy perfect for use in surgical implants such as hip balls, sockets, heart stents, and dental implants. Titanium in sporting products. The high strength of weight ratio of titanium makes it ideal for use in a wide range of sporting equipment. Titanium is a core material in the components of the world's lightest bicycle, which weighs only 6 pounds. Considering an average adult bike weighs around 30 pounds and racing bikes weigh around 15 pounds, this bike that's made out of titanium is extremely lightweight thanks to the titanium structure. The number one consumer of titanium for sporting goods is in manufacture of golf club heads. Most manufacturers are TaylorMade, Cobra, Ping, and Integra, and all of them have a titanium line. This is a picture of all the stuff that titanium is used in everyday products, and these are my 5 resources. Thank you.